Hi guys. So we're just about halfway through Unit 4. Over winter break you studied the relationships between a function and its derivative and its second derivative. And then you came back to school and we started our semester talking about position graphs. And position graphs were one application of the derivative, first derivative and second derivative, that allowed us to talk about velocity and acceleration. After that, the second big application of the derivative was optimization, which is where you're trying to maximize or minimize something. Today's video is going to start a topic called linearization. This is lecture 4.5a. By the end of this lecture, you should be able to write a linear function that approximates a curved behavior near a particular point. And that sentence is what we mean when we say linearization. So by the end of the video, you should be able to do linearization. Let's start by reviewing what differentiability is. So way back when, we talked about a curve being differentiable if the derivative on the right-hand side equals the derivative on the left-hand side. And that definition basically was the same thing as saying, at a point, if the slope on one side is the same as the slope on the other side, we consider the function to be differentiable at that point. A function is differentiable all over the place if every point fits that description. Well, there's another way to really phrase it. Another way to say differentiable, or another way to understand what it would mean for the derivative to be the same on both sides, is this statement right here. And this is where we start understanding linearization. Differentiable curves are locally linear. The idea is, if you take a differentiable function, if it really is differentiable, then if you zoom in close enough on any particular point, eventually that point and the function going through it will look like a straight line. So actually this square graph right here is a zoomed in version of this curvy function. And sure enough, when you get really close to the point 3, 0, this function, which looks perfectly curvy in a normal window, turns out looking really linear. Let me show you in Desmos if you don't believe just the pictures. Here's a bigger picture of that same cubic function. Looking at the point 3, 0, I would guess this function is differentiable at this point because it looks like the slope is the same on both sides. But the rule that we just learned was if it really is differentiable, it must mean that the function looks like a straight line going through that point. Right now, it doesn't look like a straight line, so I'm going to zoom in. And as I zoom in, sure enough, when I get close enough, when I look at a local region, a region nearby, eventually this curved line straightens out. And that proves, sure enough, that it is differentiable. And it also means that this function is locally linear. Basically, locally linear is really just another way of saying differentiable, but it allows you to think of differentiable in terms of a graph. In fact, if a function is locally linear, we should really be able to write the equation of a line that looks almost exactly like the function when you zoom in on that point. Look at this graph right here. Notice the weird units. What line does this look like? Could you write an equation for it? How would you figure out its slope? What other information would you need? Right, so we have a point 3, 0, and we can use point slope form if we can just figure out what the slope is. And when I look at the slope, it looks like even though the increments are going by 0.1 each time, it looks like this slope is -1, and that's because it goes down 0.1 over 0.1, down 0.1 over 0.1. When I make the fraction, that is a slope of 1. Okay, let's test this out for a second here. I want you to open Desmos in a separate tab. The video's about to pause. Use Desmos and check each of these functions at the indicated x values. Are these functions differentiable or not? Use the definition that you just learned on the last slide. Perfect. So when you graphed f and g, you should have seen that eventually they both turned into linear-looking functions. Now, to be clear, they didn't actually turn into lines. It's just that they looked like lines when we got really close. We would say f of x is locally linear near 2, and we would say g of x is locally linear near 4. as well as a lot of other points, but 2 and 4 as examples. H was different. When you zoomed in on H, you saw that it was still having that cusp or corner, no matter how close you got to -1. That's why h of x is not differentiable. And another way of saying it in terms of this unit is h of x is not locally linear. Now that you know what it looks like to be locally linear, we can actually get on to linearization. Remember, linearization in the objective was when you write an equation of a linear function. And to be specific, the reason we would write that linear function is because it can be used to approximate a curved function when you're really close to a particular point. Look at this graph. We've got a curved parabola in green. And we've got a tangent line at the point 2, 4. What you notice about the tangent line is that it's a linear function. And when I'm really close to the green line, the linear function looks like it's basically the same thing as the curved function. This black line is the linearization. The idea is if the line's graph is close enough to the actual function, then we can use the line and we can plug in x values to our linear function, which generally is easier than plugging in x values to other functions, and we will get outputs or y values out of the black function that are really close to the outputs or y values of the green function, which is the original function. Let's do an example. Example 1 says, find a linear function that approximates the behavior of this parabola near x equals 2. So we've got this function. What is my answer going to look like? Again, read the question if you need to. Exactly, my answer is going to be a linear equation, which I've just put in point-slope form. If I'm going to come up with a linear equation, what information do I need? Right, I'm going to need a point, and then I'm going to need to know the slope through that point. Basically, we're finding the equation of a tangent line. Well, the nice thing is in the problem we're given that the x value of the point should be 2. So all I need to do is find the y value. How do I do that? Right, we just plug in the x value to the original function because we're looking for a point that's on the original function that's also going to be on my linear function. It's the point they share right there. Now we need the slope of the function at that point, which is going to be the slope of my tangent line. How do I find it? Exactly, we take the derivative at 2, which means really at first I take the derivative of the function, and then I plug in 2, and I get that the slope is 3. So I've got x and y and the slope. All I need to do is set up my linear equation. It looks like this. And for the purpose of these questions, since it's asking for a linear function, we do actually want to convert to slope-intercept form so that we can write it in function notation. So go ahead and distribute the 3 and then add the 4. You should get y equals 3x minus 2. And then I'm going to write that using function notation, and I'm going to use an L for the linear function. I just replaced y with L of x, and that's just choosing a name L for the function. I like it because L is for linear, and this is the linearization of our function near x equals 2. And think about that language really carefully. You might want to put that in your notes. That's how we talk about it. This function is the linearization of f of x equals 1/2 x squared plus x near x equals 2. Follow my lead and find these two. Great, so this is probably not easy yet, but it should just be a series of simple steps. I'll scroll through example 2. Please pause the video if you need to spend more time looking at the answers or the work. I expect you to be able to do this by tomorrow's homework quiz. How about example 3? Right, so this was quite similar. If you got tripped up, it might have been evaluating the natural log of e squared. Remember from algebra 2, the natural log function is saying e to what power equals what's inside. So if we say e to what power equals e squared, the answer is clearly 2. Another way to think about this is that the natural logarithm and the exponential are opposites, so they cancel each other out, and the answer is just the exponent 2. Be careful taking the derivative function right here. It was a chain rule, as was the last one. And then your final answer should be a function format. Again, please pause or go back, look at the work, whatever you need to do. You need to stop and understand this. This is a shorter video. You have to do the work to make sure you understand it all. So one reason linearization is useful is because it's helpful for estimating messy functions. You actually saw examples of this in class today when you were estimating square roots. Another example would be like the cosine function. Suppose I asked you, what is cosine of 1.75? And then I told you, you can't use your calculator. Well, currently, we have no way of understanding what cosine of 1.75 would be. But linearization is actually going to give us a way to answer that question. In example 4, the question says to find a linearization of this function. Well, that's pretty familiar by now. We get that. That means find a point, find its slope, and come up with an L function that's linear. The difference is, in this example, we're not given the x value of the point. We have to choose the x value of the point. And since we want to estimate cosine of 1.75, we're going to choose strategically. In fact, I'm going to skip this part of the problem and talk about the answer for a moment. Ultimately, what we would want is we want to be able to say that cosine of 1.75 is approximately the y value that we get when we plug in 1.75 to the linear line L. Think about it graphically. Here's your cosine function. 1.75 would be just about here, and it looks like the y value of cosine should be a negative number, a small negative number. Since I don't know what that is, I'm going to create a linear function that goes through the cosine function near to 1.75. That means I need to pick an easy point nearby. In fact, there's a really good choice. What point do you know is on the cosine function that's near x equals 1.75? Sure, you know this point right here. This is pi over 2. So I'm going to use pi over 2, and I'm going to find the equation for a tangent line, which is this blue line. And then I'm going to zoom in here so you can see. And then I'm going to plug in 1.75 into the blue line. And as you can see from this picture, the answer should be really, really close to what cosine equals. Let's do the algebra. First of all, you should remember that we picked a point just based on proximity to 1.75. Right, we picked the point pi over 2 comma 0. It's a point on the original function. Now we need to know the slope of a tangent line. That's easy. We just take the derivative of the original function and plug in pi over 2. And we get a slope of -1. Now I put it all together in a linear function. And you can see I squeezed in point-slope form right here, but then wrote my function in slope-intercept form. And this equation right here, that equation is the equation of the blue line, which is the tangent line. So to estimate the red line, which you can see is really close to the blue line, we're going to go ahead and plug in. Since I can't plug in 1.75 to cosine in my head, I plug in 1.75 to the linear function. It looks like this. Notice I estimated pi, and I come out with an answer of -0.18. That's my estimate. I'm estimating cosine of 1.75 to be approximately -1.8. You can confirm that this is a pretty good estimate, either by going to graphing calculator, or if I come over here and actually look on the cosine function for the point near 1.75, you can see that we're actually quite close. Try number 5, and then I want to show you one last skill. And here's a quick glimpse of my work for 5. The last thing you need to know is how to tell whether your linearization is a good approximation. Since I'm almost out of time, I'm just going to show you the work. Please copy this into your notes, and we'll talk about what it means in class. This